Hello everyone, I am SJBIT working as a assistant professor in the department of ECE SJBIT. In the previous video I have explained about AM wave generation and detection concept. So we'll understand what are the disadvantages of AM. One is the power wastage and another one is the larger bandwidth. Power wastage in the sense the total power transmitted by an AM wave, it is usually given by PT is equal to PC plus mu square by 4 PC plus mu square by 4, nothing but PT is equal to PC plus P USB plus PLSB. PC is carrier power, USB is the upper sideband power, LSB is the lower sideband power. So in this equation what happens is the carrier component actually does not contain any information. Only the sidebands carry the information, and both sidebands carry same amount of power. So what happens is when both are like the same information carrying components, so it's a waste of power. So hence only one sideband is sufficient, another one is a redundant one. So the power wastage is more. So this is the one disadvantage of AM. The other one is the larger bandwidth. The bandwidth required is 2 times of FM. So this is because of the simultaneous transmission of both the sidebands, out of which only one sideband is sufficient to convey the complete information, but still 2 sidebands are being carried out. So thus the bandwidth it is actually the double what is being utilized. It is also been said that bandwidth is a very important parameter to be noted. So keeping all this in mind, in order to take off or to overcome the drawbacks of AM, we have a method called as DSBSC. DSBSC in the sense double sideband suppressed carrier modulation, as the name itself tells us, double sideband. So those two sidebands are sent across and carrier is suppressed. So using this technique we are reducing the power consumption. We are reducing the power consumption. When the carrier is amplitude modulated by a single sine wave, the resulting signal, it consists of 3 frequencies, as I said, that is the carrier frequency and 2 sideband frequency. Since carrier is not carrying any information, it can be omitted. That is what we are doing here. Okay. So that concept is DSBSC, where no power is wasted on the carrier, only the power is invested only to carry the sidebands, so that it becomes stronger over the longer distances. So DSBSC, double sideband suppressed carrier signal. How do we obtain it? It is actually a multiplying, or you can say product of the message signal x of t and the carrier signal c of t. So we will have a device called as product modulator, which is required for the generation of the DSBSC wave. So this is what is a simple diagram to illustrate the DSBSC modulation, where you have a message signal x of t and a carrier signal cos omega ct, or you can say AC cos omega ct. You have a product modulator. So when these two signals are multiplied, you will get x of t into cos omega ct. So this is a modulated signal, or you can say DSBSC signal, and then that will be transferred across the channel. So there are basically 2 types of generating the DSBSC. One is the balanced modulator, another one is the ring modulator. Balanced modulator is not in the syllabus. You have the ring modulator. So what we'll do is we'll directly jump into the ring modulator. So what is a ring modulator? The circuit diagram is shown like this, where you have 4 diodes D1, D2, D3 and D4, and you have a input transformer named as T1 and you have output transformer you named as T2. The carrier signal, it is represented here. It is assumed to be a square wave. You can see the symbol here. It is a square wave with certain frequency Fc. If you observe the diagram, the carrier wave, it is connected between the center taps of the 2 transformers. The output, it is obtained at the secondary of the transformer T2, that is over here. DSBSC output is obtained here. Here also, since we are going with a nonlinear devices like diodes, we will assume certain things, that diodes are ideal and they act as a perfect switch, no delay. Means it's on and off, they are actually controlled by the carrier signal. So here the ring modulator, it is operating in 2 modes. One is without modulating signal x of t, another one is with modulating signal x of t. So here in mode 1, what happens? We'll assume that the message signal, modulating signal, yes, it is absent and only we have a carrier signal m of t. So only carrier signal c of t is present, message signal is absent. So during the positive half cycle of the carrier, when c of t is in the positive half cycle, what happens? D1 and D2 are forward biased, D3 and D4 are reverse biased. So now the current flowing through the, means here D1, D2 forward biased, means the current is flowing in this direction and then here, then no, it starts from here, it goes over here, comes here, this way and this way, both. Okay, so at the center tap transformer, it is getting splitted to both the sides. The current flowing through the primary windings of the output transformer T2, now if you observe, they are equal and they are opposite to each other. So the magnetic field produced by these currents are equal and opposite. So when they are equal and opposite, they get cancelled each other. So what happens? The voltage induced in the secondary transformer, it is 0. So the output of the ring modulator is 0. This is the first case when C of t is positive. So what happened? The carrier C is suppressed. Carrier is suppressed. In the negative half cycle, what happens? D3 and D4 are forward biased. You can see, I'll mark it with a blue sketch. So the current starts from this point at the negative half cycle, plus like this, it goes on and it splits up both the way. It comes over here, D4 comes meet here. So this one, D3 comes meet here. So in this cycle, D3 and D4 are forward biased, D1 and D2 are reverse biased. The current which is flowing in the upper and lower half of the input transformer. This one, upper and the lower half of the input transformers, that is T1, they are equal and also they are opposite, right? So what happens? Again, the magnitude is created by these currents, they are equal and they are opposite, so they get cancelled each other. So again, C of t is equal to 0, so the carrier is suppressed. Again, output will be 0. So what happened now? When message signal is not present, when you have a positive half cycle and negative half cycle of the carrier, in both the case, the carrier is suppressed. In the second mode, that is when you have a message signal, that is with the message signal x of t. So now what happens? When the modulating signal is present, it is applied to the primary of the T1. Here, it is applied to the primary of the T1. So this appears across the secondary of the T1, that is here. So there are many cycles of carrier signals in positive half cycle of m of t, and same during the negative half cycle of m of t. So we need to understand when m of t is positive, what happens. When m of t is negative, what happens. When m of t is positive in its half cycle, so during the positive cycle of the carrier, D1 and D2 are on. D1 and D2 are on. Then during negative half cycle, D3 and D4 are on. This means this, I'll mark it, this one, this one, this one, this one. In all these cases, in the positive half cycle, here D1 and D2 are conducting. Okay, when x of t is in the negative half cycle, what happens at this point? Here, 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 here. Here D3 and D4 are conducting. Similarly, when m of t is in the negative half cycle, what happens? D3 and D4, here, these are all the representation because of D3 and D4 being on. They will conduct. They connect the secondary of T1 to the primary of T2 with reverse connection polarity. So what happens? This results in the 180 degree phase shift. So in Rang modulator, carrier wave, it is represented in a square wave, and you have an equation for C of t. So C of t is given by this one. It is done, general equation, but in specific, when you take DSBSC equal to 4 by pi into m of t into cos 2 pi f c t. So after taking the Fourier response, Fourier transforms, you will get this equation, and this is what is the spectrum of DSBSC, where you have the terms at Fc plus Fm and Fc minus Fm. So how do we do the demodulation then? We have generated the modulation output. How to do the demodulation? Demodulation type of DSBSC is coherent detection. So again, the same procedure. You have a modulated wave S of t, you have a locally generated oscillator, you have a product modulator, you have a low pass filter, because we are getting back the message signal which is of very low frequency, V out of t. So DSBSC wave S of t is applied to a product modulator in which this of t is multiplied with the locally generated carrier wave having the phase cos of, having the signal cos of 2 pi fct plus phi. So after doing the multiplication, they are passed through the low pass filter. So this method of detection, we call it as a coherent detection, or you can call this as a synchronous detection. So it is assumed that locally generated carrier, this one, it is synchronized in both the frequency and also the phase of the carrier signal, original carrier signal C of t, which we have used to generate DSBSC signal. So what is the output of the product modulator? V of t. So it is a multiplication, V of t is equal to S of t into C of t. So S of t is what? It is actually AC into M of t into AC dash into cos 2 pi fct into cos 2 pi fct phi. After applying the cos A cos B formula, you will get the output V of t. Then again, it contains certain unwanted terms. So if you just remove the unwanted terms after passing it through the low pass filter, it removes the high frequency component. So the output what you get is V out of t. It is Vm into Vc. You can also take it as Am into Ac into M of t into cos 2 pi fct. Actually this is 1 by 2, maybe scaled up. The output voltage of the coherent demodulator, it is only proportional to the message signal. Suppose if phi concept, here it is cos 2 pi f, no, it is phi. If the phase error is constant, so phi is a constant, so you can take this as V out of t is equal to 1 by 2 AC AM M of t into cos phi. So now you need to understand the quadrature null effect, that is when phi is equal to 0, what happens? Cos 0 is what? 1. So when there is no phase error, you will get V of t is maximum. V out of t is maximum. Suppose if you had any phase difference like plus or minus pi by 2, in that case cos pi by 2 is what? 0. So the whole output becomes 0. So this effect we call it as a quadrature null effect of the coherent detector. So hence this quadrature term, it represents the phase difference of say 90 degree, or you can say pi by 2 radians. In terms of radians, it is pi by 2. So next we will be discussing about the SSB, and that is what is the drawback of DSBSC. It transmits two sidebands which carries equal power, which carries the same information. So double the bandwidth is used. In order to overcome this drawback, we'll use this single sideband suppressed carrier where only one sideband is passed on, another will be filtered off. So that I'll take up in the next video. So in this video, I have discussed about the DSBSC wave generation method and then detection method. Both the method, why is it done, What is the purpose of going for DSBSC? Again, what is the drawback of DSBSC? How to overcome it using SSB modulation. So these are all the things we have discussed. So we'll meet up in the next video. Thank you.